Today, we are diving deep into k-means clustering. It's this incredible technique that machines use to find hidden groups and patterns in what just looks like a total mess of data, turning all that chaos into some really clear insights.
So, have you ever wondered how your streaming service can recommend the exact same show to you and, like, a million other people? It's like they've created this secret viewer club out of nowhere. The thing is, they never actually ask you what you like. They just figure it out. And they do it using powerful techniques just like clustering.
And that leads us right into our first big idea here, learning without labels. This is all about finding the natural structure in your data when you don't have some pre-made answer key to check your work. The fancy term for this is unsupervised learning. And honestly, the best way to think about it is to imagine someone just handed you a massive, jumbled box of Legos. What's the first thing you do? You'd probably start sorting them, right? All the reds over here, the blues over there, maybe squares in this pile, long skinny pieces in that one. You're finding the natural groups all on your own, without any instructions. That is exactly what a machine is doing with data in unsupervised learning.
Now, to really get what unsupervised learning is, it helps to see what it's not. So here we're comparing it to its counterpart, supervised learning. Think about something like spam detection. That's supervised. The data comes with labels already. This email is spam. This one's not spam. The goal is to predict. But with unsupervised learning, it's totally different. The data is a mystery, it's unlabeled, and the whole goal is discovery. It's about finding those hidden customer groups that you didn't even know existed.
Okay, so now that we've got that idea of unsupervised learning down, let's bring out the star of our explainer today, k-means clustering. It's one of the most popular go-to tools for doing this exact kind of pattern finding. At its heart, the idea is brilliantly simple. K-means just takes all your data and chops it up into a specific number of groups, we call them clusters. And the whole point is to make sure that everything inside one group is super similar and really, really different from the stuff in all the other groups.
So how does it do this? Well, k-means uses this key concept called a centroid. You can think of the centroid as the heart or the center of gravity for a cluster. Going back to our Lego analogy, if you've got a big pile of red bricks, the centroid is like that one perfectly average red brick that best represents the entire pile. Mathematically, it's just the average location of all the points in that cluster.
But how does the algorithm know which pile to put a Lego brick in? Well, it measures distance. The most common way is something called Euclidean distance, and don't let the fancy name fool you, it's just the straight line distance you'd measure with a ruler. The closer a data point is to a centroid, the more similar the algorithm thinks it is. Simple as that.
Okay, so we've got our key ingredients now. We've got clusters, centroids, and distance. Let's actually walk through how the k-means algorithm puts all of these pieces together.
It's this really elegant repeating process. So first up, you have to decide on k. That's just the number of clusters you want to find. Then the algorithm just randomly drops k centroids into your data. Step 3, it looks at every single data point and assigns it to whichever centroid is closest. Then, step 4, it recalculates the center of those newly formed groups and moves the centroids. And here's the magic. It just keeps repeating those last two steps, assign, update, over and over, until the groups settle down and the centroids stop moving.
So this is what we're aiming for. A good clustering result has two main qualities. First, the clusters are compact. You can see all the points are huddled tightly around their centroid. And second, they're separate. There's clear daylight between the different groups. The opposite of that, of course, is a bad result, where everything's spread out and the groups just kind of bleed into each other.
Now, this all sounds pretty slick in theory, right? But in the real world, using k-means comes with a few challenges, a few gotchas that you absolutely need to know about.
And the biggest one, the one everyone asks first, is this. How in the world do you know how many clusters, how many k, to even look for? I mean, this is the most critical decision you make. If you get it wrong, you could end up telling a marketing team to lump their budget shoppers in with luxury buyers, and you can imagine how well those campaigns would work.
Luckily, we aren't just guessing in the dark. There are techniques to help, and one of the most popular is called the elbow method. The whole idea is to try out a bunch of different values for k and see how much better things get. You're basically looking for the point of diminishing returns, that elbow in the graph, where adding yet another cluster doesn't really help you out much anymore.
So let's look at this chart here. It's plotting a score called WCS, which is just a fancy way of measuring how tight and compact the clusters are. Lower is better. Now notice that huge drop when we go from 2 clusters to 3. That's a big improvement. But then, look at the drop from 3 to 4. It's tiny. That sharp bend at k equals 3, that's our elbow. It's a huge clue that 3 is probably the best number of clusters for this particular dataset.
And there are a few other things to keep an eye on. Where the centroid start is random, so a bad start can actually lead to a weird result. You also have to be careful with features on different scales. You don't want a huge salary number to totally drown out a simple 1 to 5 star rating. Outliers, those really extreme data points, can literally drag your centroids off course. And finally, you have to remember that standard k-means is built for numbers, not for categories like Android or Apple.
All right, we have been deep in the weeds of the theory. Let's pull back up and talk about the real world. Why does any of this actually matter? Where is k-means making a difference right now? And trust me, the applications are literally everywhere. In marketing, it's the classic tool for customer segmentation to create targeted ads. In healthcare, it can group patients with similar symptoms to help doctors make a diagnosis. Tech companies use it to sort news articles by topic, and it can even be used in image recognition to find all the pictures of, say, beaches in a massive photo library. But here's something really important to remember. K-means is a fantastic tool, but it is not a magic hammer for every single problem. It's great at finding nice, roundish clusters, but for more complex, weirdly shaped data or data with a lot of noise, you might need a different tool from the toolbox, like dbScan or hierarchical clustering.
And this really gets to the core value of it all. The goal is not just to make groups for the sake of making groups. It's about providing structure to complex data. It's about revealing those hidden relationships and ultimately turning a messy pile of information into something that helps us all make smarter decisions.
So I'll leave you with this to think about. As we generate more and more data every single day, what hidden groups are just waiting to be discovered in our own lives? What kinds of patterns at work, in our communities, maybe even in our own personal habits, could an algorithm like k-means finally help us to see?